Houston, how did it go, over?
The potential for catastrophe during re-entry has plagued engineers and scientists since the dawn of manned spaceflight. By the early 1970s, when the last Apollo astronauts fell safely through the atmosphere surrounded by fire, it seemed the difficulties had been overcome. Man had conquered the moon, and NASA engineers were asking, what next? Their answer was to build a reusable space vehicle. By 1981, after nearly a decade of political wrangling, design challenges, and engineering setbacks, NASA completed the space shuttle. Roughly the size of a DC-9 jet, the space shuttle can carry a crew of up to 10 astronauts and scientists to and from space. Its cargo bay is capable of handling 27,000 kilos of payload, enough to hold satellites, carry out scientific experiments, and serve as a platform for constructing the International Space Station. But to ensure the safe return of the payload and crew, the shuttle cannot simply fall out of its orbit and aim for the ocean like the Apollo capsules before it. Once inside the atmosphere, it must glide thousands of kilometers and land on a runway. Its delta-shaped wings, capable of withstanding hypersonic speeds, provide the necessary lift. In the spring of 1981, the design was put to the ultimate test. It worked. Blasting a 2-ton vehicle to an altitude of over 300 kilometers above the Earth requires intense power.
To get anything into orbit, you've got to do two things. You've got to get several hundred miles above the surface of the Earth, and then you've got to get going fast enough so that you stay in orbit rather than just falling back to the Earth.
The amount of energy contained in a fully fueled shuttle is roughly the same as that of a small nuclear weapon.
Every time I've gone through a launch, this feeling of power, just sheer power, is overwhelming. And of course, I'm sitting there just hoping that everything holds together, because harnessing all that power really stretches our technology to the limits.
It takes nearly 2 million kilos of rocket fuel to push the shuttle into orbit and to allow it to reach a speed fast enough to counteract the Earth's powerful gravitational pull.
In order to stay in orbit, you have to be moving at 18,000 miles an hour. That's roughly 5 miles every second. That's fast. Once you're in orbit, there's nothing to slow you down. We turn the engines off. That's when you become weightless. There's no more acceleration. You stay at a constant velocity, constant speed, going around the Earth.
But to get home, the shuttle has to bleed off nearly all of that velocity. And it has to do so without power.
All of that speed, all of that energy has to come out as drag. That is the only way it gets taken out. If you were in a canoe and you put that paddle in straight down with the blade, perpendicular to the boat, you feel a force, and it slows your canoe down very fast. That's drag. Same kind of thing with the shuttle.
The difference is that the shuttle moves through the atmosphere at 25 times the speed of sound. Hitting air molecules at that speed creates tremendous amounts of friction and superheated gas.
During re-entry, you are moving through the atmosphere at thousands of feet per second. You're at hypersonic velocity. The gas outside the shuttle is at a temperature of thousands of degrees. So it's hitting the shuttle like a blowtorch.
For a crew inside the glowing space shuttle, the light show is dazzling.
Is that us that's glowing like that? Yeah. Wow, wow, wow. They're spectacular.
Though spectacular to look at, the nearly 1,600 degrees superheated air is potentially lethal. But taking an unpowered vehicle traveling at 8 kilometers a second out of orbit and guiding it to a predetermined landing strip halfway around the world is anything but routine.
You know, the old Mercury, Gemini, Apollo capsules, they had parachutes. They could land anywhere in the ocean, so you had a pretty big target you were going for. Whereas with the shuttle, if you don't land on a runway, and it better be a long runway, so there's a very limited number of runways around the world that we can land at, you're not going to make it.
To get home, the shuttle relies on gravity to pull it towards the atmosphere. But to leave its orbit and begin the descent towards Earth, the shuttle has to first slow down, and not by much.
In order to change our orbit enough so that the lower part of the orbit intersects the atmosphere, we only have to slow down by a few hundred feet per second. So that's, you know, it's a percent. It's really a very small change in total energy. But that makes all the difference, because once your orbit intersects the atmosphere, now you start to run into lots of air molecules, and they create a lot of friction, and they're going to start slowing you down in a hurry.
Before falling towards the atmosphere, the crew need to position the shuttle upside down and turn it tail first into the direction of its orbit. Then, the shuttle's orbital maneuvering system, or OMS rockets, begin to fire. In a few minutes, the 2,700 kilos of thrust generated from each engine slows the orbiter down enough to rip it from its orbit. Now, the shuttle can begin its descent. The clock is ticking, and there is no turning back.
And the first part of the deorbit is what we call this free fall trajectory. You're still weightless, but you are getting closer to the Earth. And during that time, you have to get the shuttle in the right orientation so that when you do start to get deeper into the atmosphere, you'll be able to fly.
Deciding when and where to begin the deorbit burn is an exact science. When the shuttle eventually reaches the atmosphere, it must hit a narrow corridor that will put it on a path towards the runway.
Not only does the runway have to be in front of the vehicle, but it has to happen with a certain sense of timing, because you can't be too far away from the landing site or too close to the landing site.
If the shuttle enters the atmosphere close to the runway, the steep angle will cause it to heat up too quickly from friction. It will then disintegrate. If it enters the atmosphere at too shallow an angle, the wings will begin to generate lift. The shuttle will skip off the atmosphere like a rock skipping across a pond. To fall on a precise course, the autopilot steers the orbiter by using 38 small rockets called the Reaction Control System. Located in the nose and tail sections of the shuttle, these rockets fire in quick bursts and in any necessary direction. Maneuvering the vehicle requires only 11 kilos of thrust.
Sounds pretty small, but in space there's no friction to stop the shuttle from moving around, so a 25-pound rocket does the trick.
Engineers design each re-entry so that once the vehicle hits the atmosphere, it is less than 8,000 kilometers away from the landing site. But maintaining a precise trajectory while falling towards the Earth is only part of the challenge of re-entry. The shuttle must bleed off nearly all of its speed, and it must do so at a precise rate.
One of the critical things to realize about a shuttle re-entering is that it's a glider. It has no power. So you start your re-entry with a certain amount of energy, a certain velocity. You've got to use that energy to get you to the runway. If you don't have enough energy, you're going to land short. If you get to the runway and you have too much energy, you're going to be going too fast for a safe landing. So energy management is absolutely critical.
The unpowered orbiter must generate enough lift under its wings to enable it to glide nearly 8,000 kilometers to a landing site. It must also generate just enough drag so it can slow down from Mach 25 to a few hundred kilometers an hour without getting too hot from the friction. Using data gathered from wind tunnel tests, engineers find that to achieve this delicate balance, the shuttle's nose has to be pitched up at a 40-degree angle as it enters the atmosphere.
So you're playing this trade-off game the whole time. 40-degree angle of attack, we'll moderate that plus or minus 3 degrees. That's not very much to accomplish all of those goals. Stay on trajectory, keep the peak heating and the heat load all within their limits.
By re-entering at a 40-degree angle of attack, the shuttle hits the atmosphere belly first. Soon after, it is engulfed in a blanket of fire.
Basically what's happening is you're coming in so fast that a shock wave forms. It's like the bow wave in front of a ship, but magnified probably 10,000 times. The molecules of the air press in on each other closer and closer, denser and denser until they cannot get out of the way.
The heat generated from all of that friction rips the air molecules apart. All that remains are charged particles called plasma enveloping the shuttle. Temperatures along part of the surface reach nearly 1,600 degrees Celsius. But the shock wave itself, which flows just a few feet above the shuttle, burns much hotter.
It's the same temperature as the surface of the sun. It's just an absolutely spectacular visual experience to look out and see this shock wave and, you know, realize this incredible amount of energy that's surrounding you. And you're sitting here inside this meteorite that's flying through the atmosphere coming down to Earth.
For a vehicle whose underlying structure is made of an aluminium alloy, similar to that of an aeroplane, exposure to that kind of heat would be catastrophic. Aluminium starts to soften at just a few hundred degrees. Before it reaches 1,000 degrees, it melts. To protect the shuttle and its crew, engineers had to come up with a way to shield the frame from the deadly heat.
When a shuttle is in orbit, it has energy of motion. It's going really fast. You know, just like a bullet or a cannonball has a lot of energy because it's going fast. If a cannonball goes splat against a wall, a lot of that energy is converted into heat. And that's basically what's happening when the shuttle is re-entering the atmosphere.
The plasma gas can easily melt the shuttle's aluminium frame. For engineers and scientists, keeping the heat from boring a hole through the orbiter's structure was the most difficult challenge of re-entry.
We don't want to conduct any of that heat back into the structure. We actually want to radiate it out again. We reject the heat is what we want to do. Keep it away from the vehicle.
They needed a thermal protection system capable of withstanding heat of up to 1,600 degrees. For the space shuttle, the materials also had to be reusable, something that hadn't been required before. In the early days of the space program, the Mercury, Gemini, and Apollo capsules were covered with a carbon and plastic-based material called ablatives. When subjected to intense heat, ablative material will char and burn away. As it evaporates, the resulting gas radiates into the atmosphere and away from the capsule, carrying the heat of re-entry with it. Though effective, ablatives are only good for one use. The material is expensive and it is heavy.
Obviously, you've got to get every pound you can into Earth orbit, so every pound that you wind up putting on a heat shield is 1 pound less you can taking payload to space. So the lighter the weight, the better all the way around.